Okay, this is Mathman here, and we're going to be looking at, I think, one of our last topics before we move into differential and integral calculus, and that is the topic of vectors. Now, a vector is a mathematics that was devised to represent or to deal with problems involving physical phenomena that are represented by, let's say, two characteristics. For example, force. A force is represented by magnitude, the strength of the force, and the direction that force is applied. So there are other physical entities like that, like velocity. It has a magnitude, how fast you're going, and a direction. And there are many other types of physical phenomena that display these types of characteristics in which vectors, uh, even though they seem to be a little bit more of a complex way of performing mathematics, actually simplify problems. Engineers use vectors quite a bit, looking at force components and so on. When they design structures such as bridges and other things, they have to understand how the forces work. Whenever they're designing an aircraft, they have to understand how the forces work on the aircraft. And so vectors are used in these cases to describe these type of phenomena. Now, a vector is something that can be represented both symbolically and graphically. And so it is very useful. And we have to think of a vector as something different from, let's say, temperature, which is an absolute. Temperature only has one characteristic that you measure, and that's its absolute ambient quantity, for example. It's 95 degrees Fahrenheit, or there's no direction to temperature. Temperature is just an entity um, that is an ambient quality. So we call that a scalar. It only has a magnitude, whereas a force has direction as well as magnitude. So let's take a look at this. We'll bring the camera around to the screen and to the whiteboard so that we can take a look at it. And we may not be able to cover all the vectors in this one video. There's actually quite a bit to the topic. So maybe we'll break this up into two different videos, but I do have some notes here. And so we'll start out on a graph system. And we have, let's say, an XY coordinate system. And we have our force. And forces are represented by arrows to give it a component, a directional component, and the length of the arrow represents the magnitude of the force component. So a force, let's say in this direction, with a smaller line, We'll call this force B. And they usually use some kind of a notation, a hat, or a line, or something to represent it as a vector. So a vector is represented in certain notation. We'll call this C, and we can see that B is in a different direction than C. We can see C is longer than B, so we presume then that C is a greater magnitude than B. And we can see that C can be represented as having X and Y components to it. And we can say that's x2, x1, and y2, and y1. And so we say, we represent that symbolically as C equals A 1 I. I is a unit vector that just represents the direction in which a magnitude A is. So C here is made of a component in the x direction we will call A. That's A. And also a y component we'll call B. And C then we say is equal to A plus B. And how we would represent that is if we took A in this direction and we added that to B. So B here is the same. And we put the tail of B on the end of A to add them. So that's how we add vectors. And C is the resultant vector to the addition of A and B. And so we say that A is made up of a single component because there's no y component for A. So A is equal to A1I, and A1 1 is equal to x2 minus x1. And C has also got B1 J. And J is, again, a unit vector. What I mean by unit vector is that it has a value or a magnitude of 1. So it only serves any value multiplied by itself or by 1 is itself. So it doesn't affect the magnitude of the vector. It just gives a direction. So B is equal to B1 J, where B1 is Y2 minus Y1. So this distance here is A1, and this distance here is B1. And so we represent this vector C as A1I plus B1J, and that's equal to x2 minus x1 in the I direction. They usually make that a hat plus y2 minus y1 in the j direction. I'll try and make this consistent with what mathematicians use. Okay, so let's say we have two large vectors. Let's say we'll keep the axes. Okay, so we have A, and we have B. Let's say we have B. Well, we want to find A plus B. And we say equals C. So A plus B equals C. So again, we add our vectors by putting the bottom of B to the end of A, and it's got to be in a parallel direction. That's B. And the addition, the resultant vector is in this direction. That's C. So, and we have B as x2, x1, and y2 over y1, and A is x3 and x1. So the resultant is A plus B equals, now this is A, it's x3 minus x1I plus, we didn't get the J, this is y3 minus y1 J plus, and now we represent B. B is x2 minus x1 I plus y2 minus y1 j. Now, when we add components, we can only add similar components. We only add the I component with I component and j components with j components. So let's call x3 minus x1 is equal to a1. We'll call y3 minus y1 we'll call B1. We'll call x2 minus x1 A2. And we'll call y2 minus y1 equals b2. So here we have a plus b equals a1I plus b1j plus a2I plus b2j. And again, we only add like components, I components and j components. So that's equal to a1 plus a2 I plus b1 plus b2 j. And that's a plus b, and that's equal to c. So that's how we do addition for vectors. And if we had something like a minus b, we'd have for a, we'll say a equals a1I plus b1j, and b is equal to b1I, a2I, 2I plus b2j. And so we say that we got a1I plus b1j minus a2I plus b2j, and that's equal to a1 minus a2, and that's I plus a b1 minus b2 j, and that would be a minus b. And when we do the representation in terms of arrows, we have a and b, well, we wouldn't put the b in the same direction. That wouldn't be that. We would put b in this direction, the negative direction, same length, but in a different direction, and then the resultant would be that. And we'll call this d, where d equals a minus b. So we would represent b in the opposite direction if we had a magnitude, if we had b represented in this direction. If we say minus b, then we would take b and put it on the tip of a and in the minus direction. So that's how you would subtract vectors graphically. And this is what it would mean in a symbolic sense. So let's take a look at an example of how we would add and subtract our vectors. Let's see if I can erase that so we can. Okay, let's say we have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, and we'll just enumerate them. Okay, so let's say A was equal to 3I plus 2J, and B was equal to 4I plus 3J. Okay, so we go 1, 2, 3 in this direction, and we go 1, 2. So A, this would be, oops, this would be our vector. Our vector A. Okay, B is 1, 2, 3, 4. I mean, 1, 2, 3, 4, and 1, 2, 3 up. That's the same vector. Let's give ourselves a different number. Let's say 2I plus 4J. That'll give us a different vector. Excuse me while I pick up my papers here. These notes. All right. Okay. So, I lost my screen. Should put that screensaver on a longer time. Okay, so we got most of the screen here. All right. So we got vector A. I should complete that line there. That's where I put the tape on the. Okay, boy, that's not a very good A. A. That's vector A. And vector B is 2I plus 4J. 2, 1, 2, 3, 4. Okay, so it's up here. That would be B. Okay, so we have our two vectors, A and B. If we did it added graphically, we would take B on that end and we would put it up here and then the resultant would be C. But let's just add these numerically, symbolically. So we have A plus B equals 3 plus 2I. Again, we're adding the same components, plus 2 plus 4j, and that's equal to 5I plus 6j. So our resultant would be 1, 2, 3, 4, 5, and 6. It's all the way up here. So it'd be somewhere like that. And that's our resultant. C. I don't know if I can get that line all the way up there. That would be C. And again, that's 5 and 6. And if we draw a vector from the tail of, or the end of A to C, that is B. A plus B equals C. And that's what we got. So that's how you add vectors. Now let's see what we got if we subtracted vectors. Okay, let's say we had these, and we've got these two vectors, and we got the problem A minus B. Well, A again is 3I 2j up in this direction. So we got our A and B is 2I plus 4j. Okay, so 2I and 1, 2, 3, 4. So it would be somewhere around there. Again, we're just doing this kind of crudely. And we draw our vector line up there. Magnitude and direction, B. And we're given the problem A minus B. So this would be 3 minus 2 in the I direction plus 2 minus 4 in the J direction, which would give us I minus 2J. So we would have to alter our coordinates, because we'd have to go down 2 J. So the resultant would be, let's write up here so we preserve our A equals 3I plus 2J, and B is equal to 2I plus 4J. So we can make some room here. This is our resultant. We're going to call that C. C is equal to A minus B. That's our problem. And this is our result. If we took our axis down here, let's say -1, -2, and this is 1. So our vector, our resultant vector would be right there on this coordinate system. Let's see. That would be C. 1 minus 2. And if we connected that, we would see that that would be our negative B. That would be B. So you can get the idea that you're taking, when you add, you're taking it in the positive direction parallel to your B, and when you subtract, you're taking it in the negative direction, but parallel, but in the negative direction, and then the resultant is that. And you can see the results are totally different from A plus B, which is 5I plus 6J, which was way up here. That's B, and then C would be this one that joins it from way down here. And that would be C. If C were A plus B. So we have two different conditions. We could call this one D, just so that we don't get it confused. We could call that D. D equals A minus B. So you get the idea here of how to add and subtract and what it means, because you're adding and subtracting components. Now this is all fine and good on how to add, but if we take a look at a vector itself, how do we know what the magnitude of the vector is? If we're given a vector, let's say A is equal to 10I plus 6J. And if we had some coordinate system and we had this at 0, 0 on the coordinate system, and this is 10, 6 on the coordinate system, what would be the magnitude of A? Well, we represent the magnitude with these lines. We call this the magnitude of A. And basically, if you look at if this is the X direction and this is the Y direction, you can see that we got 10 and we got 6, and we apply the Pythagorean theorem, we'll call that A, the Pythagorean theorem to this to get what we would call the magnitude, which is the hypotenuse. So the magnitude of A, or any vector, is equal to x squared. Well, what we would say is delta x squared plus delta y squared. And what do we mean by delta x? Delta x. Well, in this case, it's 10 minus 0. which is 10. Delta y is 6 minus 0, 6 minus 0, which is 6. But in some cases, let's say the vector was here and there, and this was 2, and that's 3, and yeah, this is 10 and 6. What would this vector be? Well, this vector A is equal to 10 minus 2 in the I plus 6 minus 3 in the j direction. So delta x equals 10 minus 2, and delta y equals 6 minus 3. And that's equal to 3, and this is equal to 8. So in this case, this vector would be given by the equation 8i plus 3j. Now, what do we mean by the magnitude? So we have the vector A equals 8i plus 6, or let's see, 3j. Well, we want to know the magnitude. Well, that's the change in x squared plus the change in y squared, which is, that would be 10 minus 2, that's 8 squared, plus 6 minus 3, 3 squared, and that's equal to 64 plus 9, and that's 73, square root of 73. And that happens to be 73. So what do we have? 8 times 8 is 64. 9 times 9 is 81. So it's between 8 and 9. And so we could guess that it's somewhere like 8.5 maybe. 8.5, 8.5, that's 25, 42, 48, that's 5, 2, 72, that's almost, it's about 8.6 maybe, 8.6, we can give that a try, 8.6, we'll just go roughly 8.6, 36, 48, 51, 48, 68, and that's 6, 9, 3, 7, so 73.9, so it's 8.5 something, 8, let's say 8.55. We can make a guess, that's approximately 8.55. So the magnitude of this is 8.55, because this height here is 3 and this is 8. 8 squared plus 3 squared under the square root. So that's 64 plus 9 equals 70, square root of 73, and that's what that hypotenuse is. So that's the magnitude. The magnitude of A is basically the Pythagorean theorem. not too bad. So if we're given a problem, where b is equal to 15I minus 3j, a vector of that sort, and we want to know the magnitude of b, we'd say that it's 15 squared plus -3 squared equals 15, 25, 51, that's 12, 225, and 9 is 14, 34, 234, square root of 234. And see, 20 is 400, so we'll try 10 is 100. So we'll go 16, that's 36, 9, 6, 1, that's 8, 5, 258, 16's too big, so it's about 15 something, 15, 25, 75, 5, 1, that's 5, 2, 2, 5. It's approximately 15.1, something like that. Somewhere in that neighborhood. I think that's too big. 15.1, 15.1, 151, 5. Okay, 25, 7, 151, 110, 8, 2, 1. Whoops, 12. 228. So it's bigger than 15.1, yeah, 15.2. Let's leave it at that. Approximately 15.2. I don't have the exact, I don't have my calculator with me. But anyway, the magnitude of this would be 15.2. Now, you may notice something. When we have a vector that's given on an xy coordinate system, oops, Butterfingers tonight. 1, 2, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's say we're given a vector D. That's a lousy D. Let's do C. I do C's better. C equals 5I plus 4J. And we got 1, 2, 3, 4, 5. In the x direction, I represents x, J represents y direction. And we got 1, 2, 3, 4, 5, and we got 4. 1, 2, 3, 4, so it's somewhere up here. Our vector C is represented here by this line. That's C. Okay. Well, we notice that it makes some orientation with the x-axis. And so we know here that this is 4, and this is 5, and that's 4, and this is 5. So the delta x is equal to 5, delta y equals 4, 5 minus 0, 4 minus 0, and the magnitude of C is equal to 5 squared plus 4 squared equals 25 plus 20, and that's equal to 45, square root of 45, and 7 would be 7 squared is 49, 6 squared is 36, so it's closer to 7, it's about 6.8, something like that. I'm not picking nice round numbers. Let's see, 6.8, 6.8, that's 64, 48, 54, 48, this is 36, 40, that's 4, 12, 6, 4, that's 46.24, so it's smaller. It's 6.7, approximately 6.7. 6.7 is the magnitude of C. All right, so this magnitude is about 6.7. Now, we can also say that we have a problem, what we call the dot product. Oh, well, no, even before that. Before I do the dot product, we have C equals 5i plus 4j, and we notice here we got some orientation here, and if we can see with trigonometry that with relative to this x and y coordinate system that it makes an angle with respect to x, and that would be tangent theta is equal to 4 over 5 in this particular case. So theta is equal to the inverse tangent of 4 on 5. And 4 on 5 is 0.8. So it's not quite 45 degrees. So it's less than 45 degrees. It's probably somewhere in the upper 30s, maybe 40 degrees. That's a guess. I can get a calculator and we can calculate that exactly. All right, so let's take a look at 4 divided by 5, and that's 0.8, and the inverse tangent of that is 38.6. So I was off a little bit. I was overestimated. So it's approximately 39 degrees. That was a little high. So approximately 39 degrees. So we can get that orientation there with respect to the x-axis. Now, we can do something called it's a type of multiplication that you do with vectors, and it's called a dot product. Well, first off, before that, let's take a look at a vector A. That's 5i plus 12j. Okay, I can't draw it on here because it'd be off the scale. But what if I had a scalar? Let's say a scalar A, and that's just a number. Scalar is just a number. That's all it is. And we have a scalar of 7. And we go A times the vector. That's called scalar multiplication. Scalar multiplication would be that times 7. And with scalar multiplication, you multiply all the way through by 7. So we got 35i. So a times vector A, scalar multiplication, plus 12 and 7 is 14. 84, 84j. And so that's scalar multiplication. You just multiply through. Then we have a different type of multiplication that we call dot product. And the dot product is basically a multiplication between two vectors that exist in some plane. And let's say that's A, and we have vector B, and we have an angle between them. And we say, what is A dot B? That's called a dot product. And we have A is given by, let's say, 2i plus 3j, and B equals 1i plus 5j. Okay? Just for sake, don't look at the hash marks. This is just a given problem. Okay, A dot B, we take a look at the components. So we multiply only the same components. So we take 2 times 1 I dot I and 3 times 5 j dot j. Well, I dot I equals 1 and j dot j equals 1. So that just gives you a magnitude of the I. So whenever you see that, you can even ignore it. It turns out that dot products only yield scalars. So this is equal to 2 plus 15, and the result is 17. So A dot B. Let's take another quick look at another one. Another example, let's say vector A is equal to 3i plus 4j, and B is equal to 6i minus 7j. So A dot B is equal to 3 times 6 plus 4 times negative 7. And that would be 18 minus 28, and that's equal to minus 10. Now, again, a dot product yields a scalar. Now, just one last thing before we quit. You may notice something here. that if you have A dot A, you have, let's say, A is equal to 3I plus 4J, and we have A dot A. It's like A squared in a sense. We have 3 times 3 plus 4 times 4, and that's equal to 9 plus 16. That's equal to 25. So this is like A dot A is almost like the magnitude of A squared. And in fact, because A is parallel to itself, A dot A is equal to the magnitude of A cosine of theta between them, which is 0, 0. The angle is 0, so that's 1. So A dot A over the magnitude of A times the magnitude of A equals 1. Now, if we want the magnitude of a vector, we can say that A dot A to the half power is equal to the magnitude of A. That's another nice component. Now, if you had A and B, let's keep that A, and we have B. B equals 4I plus 6J, and we have A dot B. Now, if we just do that, we have 3 times 4 plus 4 times 6, and that's 12 plus 24, and that's equal to 36. A dot B is equal to 36. But A dot B also is got the angle between it. It's the magnitude of A, magnitude of B, cosine of the angle between them. So here's the angle between them. There's B and there's A. So if we want the angle between the two vectors, we've got A dot B over the magnitude of A times the magnitude of B equals cosine of theta. Well, then we go the inverse cosine of this is equal to theta. And that's how we get that angle between the two vectors. So the dot product over the magnitudes. So let's take a look at a problem here. We got these two vectors. So A dot B over magnitude A times the magnitude of B equals cosine theta, and that's equal to 3 times 4 plus 4 times 6 over the magnitude of A, which is 3 squared plus 4 squared times the magnitude of B, which is 4 squared plus 6 squared. Okay, so let's get the math. That's 12 and 24, that's 36, over, that's 9 plus 16, that's 25, so that's 5 times, that's square root, that's 16 and 36, that's 252, square root of 52. So this is, let's see what the square root of 52 is. We'll get the 5. Okay, let's take the square root of 52 is 7.21 times 5. Okay, times 36. Okay, so that's equal to 0.998. That's almost 1. And now, if we take the inverse cosine inverse of 0.998, we're going to get a small angle because that's almost 1. That's equal to 3.17 degrees. So let's write that somewhere else. 3.7 degrees. That's cosine inverse of 0.998 equals 3.17 degrees. So that's what this angle is, 3.17 degrees. Not very big in this particular case, but that's how you would get the angle of between the two vectors. And you can see that these are not too far from each other, really. If we plotted it out, 1, 2, 3, and 1, 2, 3, 4. So there's somewhere a line there, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So it would be up there. It's just almost the same vector. So it'd be that one and that one. And this angle is only 3.17 degrees. So you can see that it makes some sense, even though my drawing isn't so good. All right, so we have we've seen some operations already. We've added, we've subtracted, we've multiplied using scalar, and we've done what we call a dot product. The next thing that we're going to have to take a look at, we're going to call it quits at this time, is we're going to look at a cross product, and that's when you have A dot or A cross B, and that's going to be what we deal with next time. The other thing is we've been dealing mostly with two-dimensional vectors, but everything also applies to three-dimensional vectors. So if we had an xy, let's get the cross product off. That's for next time. If we had x, y, z, and we had a, theta, and we had, let's say, B, and we got some angle between them, and A is given by 1I plus 2J plus 3K. K is the Z direction, and B is 3I, 1J plus 5K. And so A plus B would be equal to 4I plus 3J plus 8K. That would be something in between that goes up that way. The magnitude of A and B would be, A would be, we got 1 and we got 2. So this is 1 squared plus 2 squared. That's a square root of 5. Square root of 5. And then this height is 3. So the magnitude of A is equal to 1 squared plus 2 squared plus 3 squared. And this is equal to magnitude, or square root of 5 squared plus 3 squared equals 5 plus 9 equals 14. Square root of 14. So that's the magnitude of A. And you could do the same thing for the magnitude of B. A dot B would be equal to 3 times 1 plus 2 times 1 plus 3 times 5, and that's equal to 3 plus 2 plus 15, and that's equal to 20. And if we wanted the angle between A and B, we'll call that phi. That would be the inverse cosine of the A dot B over magnitude A times magnitude of B. And that would be equal to, well, we have to get the magnitude of A and magnitude of B. Magnitude of A we had was the square root of 14. Magnitude of B we didn't calculate, but that's square root of 3 squared plus 1 squared, and that squared plus 5 squared equals B, magnitude of B. So that is 9, 10 plus 25. That's square root of 35 is equal to the magnitude of B. So we have A dot B. What was A dot B? A dot B was 3 plus 2 plus 15. So that was 20. 20 over square root of 14, square root of 35. And that would be, we can do that calculation pretty quickly. 5813. Alrighty. Okay. 14. That's 3.74 for this. 3.74. 35 square root is 5.91, 5.91. So times 3.74 equals that times 20. And that's equal to 0.904. And so again, we have a very small angle between these two. So inverse cos of 0.904 equals, and let's take the inverse, that's 25. Let's write this over here. This phi equals that, and phi equals 25.3 degrees. So the angle between A and B is 25.3 degrees. Now, one last thing. If B and A are parallel, then B dot A is equal to 0. And let's see, A dot A is definitely parallel. So let's say A is equal to 3I plus 2J. And we got A dot A, so that's, A dot A is 9 plus 4, that's 13. Okay, so the magnitude of A is equal to 13. So if A dot A is over magnitude of A, that's equal to 1, equal to the cosine of 0 degrees. So if A and B are parallel, they'll equal to 1. When they're, let's say, their dot product equals to 1. So A dot B over the magnitude of A and the magnitude of B is equal to 1. Now, they're parallel if they're 0. So if A dot B over A, magnitude of A, magnitude of B, must equal 0 equals cosine pi on 2. So that means the angle is 90 degrees. They're perpendicular to one another if they're 0. So if A dot B is 0, then the two vectors B and A are perpendicular to one another. Okay, so we packed a lot in. I kind of rushed through it. Maybe we can review it again a little bit next time. But again, that's an important result. When the dot product of a vector is 0, parallel. Let's take a look at an example. Let's say A equals 2I plus 5J, and B equals 5I minus 2J. Okay, so we have an X and Y coordinate system. Okay, and we have 1, 2, 3, 4, 5. We have 1, 2, 3, 4, 5, 1, 2. Okay, so we got 1, 2, 5. This is A. That's A. And we have 1, 2, 3, 4, 5. 1, 2. We got down there. That's B. And we want this angle between them. Well, you can see just graphically here that it looks like they're perpendicular. But if we do A dot B, we have 2 times 5 minus 2 times 5, and that's 0. So A dot B equals 0. They're perpendicular. The angle theta will be 90 degrees. when that ratio A dot B over the magnitude of A over the magnitude of B equals 1, then we know they're parallel, that the angle between them is 0. So those are the two extreme conditions. Okay, well, we'll call it quits for the evening, and we'll pick it up next time, and we'll look at this again, cover this a little bit more detail, more examples, and we'll look at cross products. Cross products are worthy of a whole video in their own right. So this is Mathman wishing you well.